A galaxy is 99.999% empty space. And the photograph you grew up looking at, the bright swirl of 100 billion stars packed together so tightly they seem to blur into a single pool of light, is a lie. Not a deliberate lie, a necessary one. Because the truth, the actual texture of a galaxy when you zoom in until you can see what is really there, is a truth that our instruments were not built to show us, and our imaginations were not built to hold. Tonight, we are going to zoom in, not metaphorically, not in the casual way that narrators say the word zoom when they mean examine. We are going to walk, step by step, from a galaxy seen as a single bright smudge, from a dark mountaintop on Earth, all the way down to a single photon travelling through the gap between one star and its nearest neighbour. And at every step of the journey, we are going to measure what is actually in the frame, what is bright, what is dark, what is there. And the answer, the one that nobody tells you because it does not fit on a poster in a science museum, is that a galaxy is mostly nothing. A galaxy is so mostly nothing that if you removed every star, every planet, every gas cloud, every molecule of anything, the void left behind would be almost indistinguishable from the galaxy itself. If this has you hooked, subscribe to the channel so you don't miss what comes next, because this story is just getting started. Drop a comment below. I want to know where in the world you're watching from, what time it is where you are, and your honest take on this. If a galaxy is nearly all empty space, what does that actually mean for the universe you think you live in? Tell me what you think. Now, settle in because we have a lot to unpack. Part 1. The lie your eyes tell you about galaxies. Every picture you have ever seen of a galaxy is, in a precise technical sense, dishonest. Not because the astronomer who took it was trying to deceive you. They were not. Every image of the Andromeda galaxy, every deep-field photograph of the whirlpool, every panoramic mosaic of the Milky Way's disk arcing across a desert sky is a composition of real photons faithfully recorded. The dishonesty is not in the capture. The dishonesty is in the compression. When a camera, whether it is a human eye or a CCD on a space telescope, collects the light from a distant galaxy, it gathers photons that have been travelling in some cases for tens of millions of years, or hundreds of millions or billions. Those photons were emitted by stars scattered across a volume of space so large that no human metaphor can hold it honestly. But the camera does not care about the volume. The camera only cares about the direction from which the photons arrived, and all of the photons from a galaxy's worth of stars, no matter how far apart those stars are from each other in three-dimensional space, arrive at the camera from a very narrow cone of directions. They get funneled down by the geometry of the situation onto a small patch of the sensor. A patch that might measure, on a typical astronomical photograph, a few square millimeters. A patch that might measure, if the galaxy is far away, a single pixel. What the camera records is the total brightness of that patch. What it cannot record, because it cannot, is the depth of what is behind each pixel. When you look at the bright band of Andromeda on a sharp photograph, you are looking at the light from stars that are in three-dimensional space, separated from each other by distances measured in trillions of kilometers. Stars that are at the front of the galaxy, closest to Earth. Stars that are at the back of the galaxy, many hundreds of thousands of light years further away. Stars that are in the middle, at every intermediate distance. All of their photons compressed onto the same pixel, all of their distances collapsed into one apparent brightness. The result is that a photograph of a galaxy looks, to the human eye, like a fog of packed light, like a shimmer of stars so dense they cannot be separated, like a bright carpet. And this impression is so visually powerful, so immediate, that almost everybody who looks at a galaxy photograph carries away from the experience a feeling of density, a sense that a galaxy is something crowded, something full, something that, if you could somehow drop yourself into it, would surround you with stars on every side, the way a forest surrounds you with trees. This impression is wrong. This impression is wrong by many orders of magnitude. This impression is wrong in a specific, measurable way that we are going to walk through carefully over the next hour and 45 minutes. And by the end of the walk, you will understand what a galaxy actually looks like when you stop photographing it and start flying through it. What it feels like to be inside a structure that contains 100 billion stars and, simultaneously, contains almost nothing at all. The mismatch between the photographic impression and the three-dimensional reality is not a small mismatch. It is not a rounding error. It is not the kind of thing a careful observer would notice if only they squinted harder at the image. It is, mathematically, a factor of something like 10 to the 14th, a 1 followed by 14 zeros. That is the scale of the gap between what our eyes see when they look at a galaxy image and what is actually there. A gap so large that the same object, measured by two different techniques, gives answers that feel like they cannot possibly describe the same thing. Let that land for a second. The galaxy you picture in your mind and the galaxy you would encounter if you could fall into one are separated as mental models by a factor of 100 trillion. You have been carrying around the wrong image of a galaxy your entire life, not because you misremembered it, because the image you were given was not capable of being right. The reason this matters is not aesthetic. It is not simply that the popular picture of a galaxy is inaccurate. The reason it matters is that the emptiness of galaxies, the enormous distances between the things that populate them, is one of the most important facts about the universe. It explains why galaxies can pass through each other without stars colliding. It explains why light travels so freely from one galaxy to another. It explains why the universe is mostly transparent, mostly quiet, mostly dark. And it explains why the search for life, the search for signals, the search for any kind of cosmic company is as difficult as it has turned out to be. You cannot understand any of this while you still picture a galaxy as a bright carpet of stars. The first thing we have to do before we can go any further is unmake that picture. We have to replace the photograph with the reality. We have to walk into the galaxy and see what is actually there. Part 2. What 1 pixel of Andromeda actually contains. The Andromeda Galaxy is the closest large galaxy to our own. It is about 2.5 million light-years away. You can see it with your naked eye on a dark night as a faint oval smudge of light, slightly larger than the full moon. In a modest telescope it resolves into a bright elongated disk with a brighter core. In a professional astronomical photograph, stacked from many hours of exposure and filtered through multiple wavelengths, it resolves into a stunning spiral with dust lanes, star-forming regions, and 2 visible dwarf companion galaxies hanging beside it like reflections. A typical high-resolution image of Andromeda, the kind you can find on NASA's website, is composed of roughly 400 million pixels. Each pixel, at that resolution, represents a patch of sky about 1 arc second across. At Andromeda's distance of 2.5 million light-years, 1 arc-second of sky corresponds to a real distance across the galaxy of roughly 12 light-years. A single pixel, in other words, is looking down a column of space 12 light-years wide at the galaxy's face-on distance and extending all the way through the galaxy from the front to the back. Some parts of Andromeda are thin. The outer disk is maybe 1,000 light-years thick. The central bulge is more like 10,000 light-years thick. Call it on average a few thousand light-years. A single pixel represents a column of space 12 light-years wide and a few thousand light-years deep. Inside that column, how many stars are there? The answer depends on where in the galaxy you are pointing. In the bright central bulge, the star density is high enough that a 12 light-year wide column, reaching through a few thousand light-years of galaxy, might contain several thousand stars. At the edge of the visible disk, where the galaxy is thinning out, the same column might contain only a few dozen. On average, across the bright part of Andromeda, a single pixel of a NASA photograph is looking at, very approximately, 1,000 stars. 1,000 stars, 1 pixel, no way to separate them. All of their photons compressed into a single brightness value, a single number that the camera records, and the image processor displays as a single dot of color on your screen. Now ask the question you should probably be asking. If a single pixel contains 1,000 stars, how close together are those stars? How densely packed is the region of space that produced that pixel? Here is where the reality of a galaxy begins to separate from the impression of a galaxy. 1,000 stars, distributed through a column of space 12 light-years wide and 3,000 light-years deep, occupies a total volume of roughly 400,000 cubic light-years. 400,000 cubic light-years for 1,000 stars. That works out to 1 star per 400 cubic light-years. 1 star in a cube that measures 7.5 light-years on a side. 7.5 light-years. That is the distance from the Sun to a point well beyond the orbit of Alpha Centauri, the nearest star system to our own. That is further than any human-made spacecraft has ever travelled by a factor of more than 1,000. That is a distance so large that if you wanted to cross it at the speed of a commercial airliner, it would take you 6.5 million years of non-stop flight, no refueling, no sleeping, no stopping to look at the view. 7.5 light-years. That is the average spacing in the bright central region of Andromeda between one star and the next. That is the empty distance that a camera photographing Andromeda compresses into a single bright pixel. That is the fog that, from 2.5 million light-years away, looks like a solid sheet of light. Let me say that again so it registers. In the brightest, densest, most star-populated part of one of the brightest galaxies in the universe, the average distance between stars is larger than the distance from our Sun to the nearest star. And that star, the nearest one to us, is already so far away that we have never been to it, and we probably never will. If we took the entire population of 1,000 stars in 1 pixel of Andromeda and laid them out in a simple 3-dimensional grid, each star would be closer to 7.5 light-years from its nearest neighbour than to any other star in the grid. Each star would be alone in its own cube of nearly empty space, a cube bigger than the entire interstellar neighbourhood we have ever explored. This is the truth that the photograph cannot show you. This is the truth that no image of Andromeda has ever captured, because no camera can capture it without a cartographer's projection. without a walkthrough, without the patience of a narrator willing to stop and say, "This is what is really there," and to let the unreality of the picture you are holding dissolve. The picture says dense. The picture says packed. The picture says crowded. The three-dimensional reality says empty, says scattered, says alone. Part 3. The first jump. From galaxy to spiral arm. Let us start the zoom. We begin where every human being starts their relationship with a galaxy, which is from outside it. Standing on Earth, on a clear night, far from city lights, you look up at the sky and see the Milky Way. What you are seeing is our own galaxy, viewed edge-on from within, a band of diffuse light that stretches from horizon to horizon. You are inside the Milky Way. You have always been inside it. The sun has always been inside it. Every human being who has ever lived has spent their entire existence embedded within one of the spiral arms of the Milky Way, moving with it, rotating with it, carried along by its slow rotation around a central black hole whose gravity organizes the entire structure. But for the purposes of this walk, we are going to step outside. We are going to pretend as if we had a spacecraft capable of doing so, to fly out above the galactic plane by a distance large enough to see the whole galaxy at once. A few tens of thousands of light years above the sun's position, looking down, what we see, if we are patient enough to let our eyes adapt, is the Milky Way galaxy, as it would appear from above. A central bulge of old yellow stars, several spiral arms sweeping out from the bulge, curved by the differential rotation of the disk, dust lanes threading along the inner edges of each arm, dark against the bright starlight. A diffuse halo of old stars and globular clusters surrounding the disk, extending far beyond the visible structure. The whole thing, from end to end, about 100,000 light-years across. At this scale, the galaxy looks like a photograph, dense, bright, packed with stars that blur together into a continuous sheet of light. This is the visual impression we discussed in Part 2. It is the compression, the pixel-level averaging, the collapse of three-dimensional structure into two-dimensional luminance. You are too far away to see the gaps. You are too far away to see the structure. You are seeing only the sum of all the light emitted by all the stars in the galaxy, projected onto the retina of your imagination, and you are reading that sum as density. Now zoom in. As you descend toward the galaxy, the structure starts to resolve. The spiral arms, which at great distance looked like continuous bands of light, begin to show texture. The smooth sheen of starlight begins to break up into clumps. The arms themselves are not uniform. They are braided. They have knots. They have bright pockets where star formation is actively occurring and darker regions where the stars are older and dimmer. The galaxy is not a flat disk with uniform density. The galaxy is a complicated thing with internal substructure that only becomes visible when you get closer. Zoom in further. Pick a spiral arm. The arm we want to explore is the Orion Arm, the minor spur of the Milky Way in which our own sun resides. As you descend toward the Orion Arm, the arm itself begins to resolve into individual brightness centers, clusters, associations, groups of stars that formed together from the same molecular cloud, and that are drifting through the galaxy as loose, gravitationally unbound, traveling companions. Some of these clusters contain a few dozen stars, some contain a few thousand, some are visible from Earth with the naked eye as small bright patches in the sky. The Pleiades, the Hyades, the Beehive. These are real objects that you have seen, you just did not know they were pieces of the Orion Arm. Zoom in further. Between the bright clusters, what is there? The answer is the thing that galaxy photographs cannot show you. Between the bright clusters, there is space. Vast, almost empty space. Space filled with a very thin scattering of individual stars, one every few light years or so. Space threaded with filaments of interstellar gas and dust. Some of them organized into nebulae where new stars are forming, most of them spread out so diffusely that you would have to look for kilometers to find a single hydrogen atom. Space through which the solar wind of our sun flows, a tenuous bubble of charged particles extending out to about 100 astronomical units beyond the orbit of Pluto, into a region called the heliopause, where the sun's influence finally gives way to the diffuse pressure of the interstellar medium. At this zoom level, the Orion Arm is no longer a bright band. It is mostly darkness threaded with sparse stars. The clusters are bright islands in a sea of mostly empty space. The typical distance between individual stars in the arm, outside the clusters, is a few light years. And those few light years are, on the scale of anything a human being has ever experienced, a distance that collapses language. Part 4. The distance between stars in the arm. The Sun's nearest stellar neighbour is a triple star system called Alpha Centauri. It is, in astronomical terms, practically next door. You can see it from the southern hemisphere as a single bright point of light, the third brightest star in the night sky. In a small telescope, it resolves into two stars orbiting each other. In a larger telescope or in the careful measurements of a professional observatory, a third, much smaller, much dimmer star becomes visible, orbiting the pair at a great distance. That third star is called Proxima Centauri, because it is, by a small margin, the closest star to the Sun. Proxima Centauri is 4.24 light-years away. That is the distance in technical terms that light, travelling at 300,000 kilometers per second, covers in 4 years and 3 months. Let me give you a different way to think about that. A commercial airliner flies at about 900 kilometers per hour. If you could somehow build a commercial airliner that could fly through the vacuum of space and you pointed it at Proxima Centauri and started the engines, it would take you roughly 5 million years to arrive. 5 million years, without stopping, without refueling, without any maintenance, with the engines running continuously. By the time you arrived, the species that built the airliner would have evolved into something unrecognizable, or gone extinct, or both. A different comparison. The Voyager 1 spacecraft, launched in 1977, is currently the fastest human-made object ever to travel outward from the Sun. It is moving at about 17 kilometers per second, or roughly 60,000 kilometers per hour, which is about 66 times the speed of a commercial airliner. At Voyager 1 speed, the trip to Proxima Centauri would take approximately 73,000 years. 73,000 years of continuous flight. The entire span of behaviorally modern human history is only about 50,000 years. If Voyager 1 had left at the time of the first cave paintings in Europe and had been travelling continuously ever since, it would still have 23,000 years of flight left before it reached the nearest star, 4.24 light-years. That is the typical spacing between stars in the disk of the Milky Way, in the general neighbourhood where the Sun resides. That is the emptiness that separates one star from the next. That is the gulf that the bright photograph of the Orion Arm compresses into a pixel. Now, consider what 4.24 light-years looks like as a volume of space. The Sun sits at the centre. Proxima Centauri sits at the edge 4.24 light-years away. Between the two there is a sphere of space with a volume of about 320 cubic light-years. Inside that sphere, how many things are there? The Sun, 8 planets, a few dozen moons, a scattering of asteroids and comets, a vast number of small icy bodies in the Oort cloud. Beyond that, interstellar space populated by the occasional rogue planet, by perhaps a few small brown dwarfs, by a diffuse scattering of hydrogen atoms and dust grains, and by nothing else of any substantial mass at all. 300 cubic light-years between our Sun and the nearest star. 300 cubic light-years of almost perfect emptiness. If you took all of the mass of everything inside that volume, including the Sun itself, and compressed it into a single object, that object would still be dwarfed by the volume of empty space it was drawn from. The ratio of mass to volume in the interstellar neighborhood of the Sun is smaller than the ratio of a single raindrop to the total water in all of Earth's oceans. And this is the dense region. This is the disk of a spiral galaxy, where stars are relatively common. This is the arm, the bright part of the picture, the place where the photograph shows a carpet of light. In the empty space between galaxies, the density is lower still, by factors that escalate the number faster than ordinary English can keep up with. Part 5. The cubic parsec that is almost perfectly empty. Let us stop for a moment and introduce a unit that astronomers use more often than light years, even though it is less familiar to most people. It is called a parsec. A parsec is a distance of about 3.26 light-years, defined by a specific geometric relationship having to do with the apparent motion of stars across the sky. A cubic parsec, then, is a volume of space roughly 34 cubic light-years. In the general neighborhood of the Sun, the density of stars is about 1 star per cubic parsec. 1 star in 34 cubic light-years. 1 star in a volume of space that, if you tried to walk across it at the speed of light, would take you more than 3 years to traverse in any direction. 1 star in a cube of space so large that human language does not have a built-in word for its scale. What is in the rest of the cubic parsec? That is the question we should be asking, because the answer is what makes the galaxy empty. The answer is almost nothing. A cubic parsec contains, on average, about 1.5 atoms of hydrogen per cubic centimeter of space. That sounds like a lot. Atoms are small. 1.5 atoms per cubic centimeter seems numerically like not nothing, but translated into something you can feel. On Earth, at sea level, a cubic centimeter of air contains about 2.5 times 10 to the 19th molecules. 2.5 followed by 19 zeros. Compare that to 1.5 atoms in the same cubic centimeter in interstellar space. The ratio is roughly 10 to the 19th. The vacuum between the stars is 10 billion times thinner than the air you are breathing right now. And even that is the average. In particular regions of the galaxy, where interstellar clouds are drifting, the density is higher. In other regions, the intercloud medium, the density is lower. In the very emptiest parts of the galaxy, the diffuse warm ionized medium, the density drops to less than 1 atom per cubic meter. Less than 1 atom per cubic meter. That is the kind of emptiness that exists between the stars, averaged across the quieter regions of the disk. Let us try to picture what this means. Imagine you are a photon, traveling in a straight line across the disk of the Milky Way. You are moving at the speed of light. The galaxy's disk is about 100,000 light-years across. How much matter do you encounter on your journey from one edge of the galaxy to the other? The math works out under average conditions to roughly 15 grams of matter per square centimetre of your flight path. 15 grams, about the mass of half an ounce of water, spread across a distance of 100,000 light years. That is the density of matter averaged along a galaxy-crossing line of sight. That is what the photon has to push through to get from one side to the other, and most photons emitted from one side of the galaxy do, in fact, make it to the other side, because the density is so low that collisions are rare. The galaxy is transparent to itself. A galaxy is, in a very real sense, a mostly empty volume of space through which light travels almost unimpeded, with occasional bright sources, the stars, and a thin mist of absorbing matter threaded between them. When you compare this to the mental image of a dense carpet of stars, the gap between impression and reality is hard to overstate. The galaxy is emptier than anything you have ever imagined being empty. The galaxy is emptier than the best vacuum humans have ever made in a laboratory by many orders of magnitude. The galaxy is, to first approximation, nothing. 100 billion stars scattered like grains of sand across a volume so large that the grains might as well be alone. Part 6. The gulf between one star and the next. Let us zoom in further. We have already measured the average distance between stars in the Sun's neighbourhood, 4.24 light-years, roughly. That is the distance to Proxima Centauri. But that is just the closest star. Most stars are further apart from their nearest neighbours than that. The Sun, as it happens, is in a slightly below average density region of the galaxy, in a volume of space called the local bubble, which is a region of reduced gas density, carved out by supernova explosions that occurred a few million years ago. Inside the local bubble, the stellar density is slightly lower than the galactic average. The typical distance between a star and its nearest neighbour in the local bubble is perhaps 5 or 6 light years. Let us pick a direction and fly. We leave the Sun, we pass the orbits of the planets, we cross the heliopause, we enter interstellar space. What do we encounter? The honest answer is almost nothing. We pass through the diffuse interstellar medium, the thin mist of hydrogen and dust. Every few tens of billions of kilometres, we might encounter a single small dust grain, a particle of silicate or carbon no larger than a smoke particle. Every few cubic kilometres, we might encounter a single hydrogen atom. Otherwise, nothing. Vacuum so thin it is almost perfect. We fly for a light year, nothing substantial. We fly for 2 light years, still nothing. We fly for 3, 4, and eventually, after 4¼ light years of flight, we approach Proxima Centauri, a small red dwarf star, about 1/8 the mass of the Sun, dim and cool, orbited by at least 2 planets. We have arrived at our first stop. Between the Sun and Proxima Centauri, there has been nothing of any substantial mass. The journey has been, by any human standard, an empty one. Now, consider what Proxima Centauri is in the context of this emptiness. It is, in astronomical terms, a close neighbour. It is the closest other star, and it is 4¼ light years away, which means that most of the interstellar neighbourhood, the region within a few light years of the Sun, is empty. The few objects that are there are separated by distances so vast that the phrase interstellar neighbourhood is almost a contradiction in terms. A neighbourhood, in human experience, is a place where you can see your neighbours. In the interstellar sense, a neighbourhood is a region where your nearest neighbour is a spot of light that will take 70,000 years to reach at the fastest speed humanity has ever achieved. Let that land for a second. This is not a rhetorical flourish. This is the geometry of a spiral galaxy at the resolution where individual stars are separable. The stars are not packed together. The stars are not close. The stars are separated by gulfs of emptiness so large that every star is, to every other star, effectively unreachable on any timescale a biological organism can relate to. Each star sits in its own vast bubble of interstellar space, visiting the others only across spans of time that dwarf every timescale of life, every timescale of civilization, every timescale we have been given by our own existence to measure. Part 7. What light actually encounters on its journey? When we say that a galaxy is transparent to its own light, what we mean in specific physical terms is this. A photon emitted by a star on one side of the galaxy, travelling at the speed of light, can reach a star on the other side of the galaxy without being absorbed or deflected in the vast majority of cases. The photon does not bump into anything. The photon does not get scattered off of anything. The photon does not encounter any object large enough or dense enough to meaningfully interact with it. Over a journey of 100,000 light years, how rare is an interaction? Extremely rare. The cross-section of a hydrogen atom is about 10 to the minus 17th square centimeters. The density of hydrogen atoms along a typical galactic line of sight is about 1 per cubic centimeter on average, dropping to much lower in diffuse regions. Multiply those numbers together over a path length of 100,000 light years, and you find that the probability of a single hydrogen atom intercepting a given photon is somewhere around 1 in 1,000. Most photons make it across without ever encountering an atom. Most atoms sit undisturbed in their little patches of interstellar vacuum, while beams of starlight pass through them without either being affected. This is what it means for a galaxy to be mostly empty. It means that light travels through it almost unimpeded. It means that gravity is the only force that connects the stars to each other, and that connection operates across distances so large that it takes the orbital period of stars around the galactic center to be measured in hundreds of millions of years. It means that if two galaxies collide, which does happen, and is happening between the Milky Way and Andromeda, over the next several billion years, the stars of the two galaxies will pass through each other without colliding. No stellar impacts, no direct hits. The galaxies will interpenetrate like two clouds of mosquitoes flying through each other. The densities are so low that the probability of two stars hitting each other during a galactic merger is essentially zero. Zero. Think about that for a moment. Two galaxies, each containing hundreds of billions of stars moving through each other at hundreds of kilometers per second, and not a single pair of stars statistically is likely to physically hit another. The galaxies disrupt each other's shapes. Gravity pulls individual stars onto new orbits. The cumulative tidal forces reshape both galactic disks into wild plumes and streamers, but the stars themselves never touch. The emptiness is so thorough that even in the most violent galactic event short of a merger with a supermassive black hole, individual stars are safe. This is one of the stranger facts about the universe, and it is also one of the most reliable. The emptiness protects us. The vast interstellar distances mean that whatever happens elsewhere in the galaxy, most of it does not reach us. Supernovae explode, neutron stars collide, black holes accrete matter with spectacular violence, and we, embedded in our corner of the Orion Arm, mostly watch it all from far away, receiving the filtered, diluted, distant light as we go about our small-scale lives on a small-scale planet around a small-scale star. The interstellar medium is, among many other things, a kind of quiet room, a cosmic soundproofing, a void that softens everything. Part 8. The density illusion explained. By now, you may be asking a reasonable question. If galaxies are mostly empty, if stars are separated by gulfs of light years, if the density is so low that even galactic collisions do not produce stellar impacts, then why do galaxies look so bright? Why does the photograph of Andromeda show such a thick carpet of light? Where is all the light coming from, if there is so little there? The answer is a subtle one, and it is the answer that ties together everything we have walked through so far. The light comes from a huge number of stars, each one of which is very bright in its own right. One star, like our Sun, is an unimaginably powerful object. The Sun emits about 4 times 10 to the 26th watts of energy continuously for billions of years. That is a quantity of energy so large that it defies everyday comparison. It is the output of several billion of the largest nuclear power plants humans have ever built, sustained for the age of the Earth. One star. Now multiply that output by 100 billion stars. Now consider that all of the light from all of those stars is being emitted continuously, every second, for the lifetime of the galaxy. Now consider that the light, although diluted by distance, still reaches us in enormous total quantity. Because the galaxy is large and the aperture of our telescopes is large, and the total integrated light from 100 billion stars is, even after the dilution of distance, a detectable and even bright thing. In other words, the galaxy is bright because of the number of stars, not because of their density. 100 billion very bright things spread across a very large volume still produce a lot of total light. The light, compressed onto a two-dimensional image, creates the impression of density. But the density is an impression. The galaxy is bright and mostly empty at the same time. These two facts are not in conflict. They are two different measurements of the same object, viewed through two different techniques, producing two different but equally true descriptions of what is there. It is the difference between a photograph and a walkthrough. A photograph captures integrated light. A walkthrough captures three-dimensional occupancy. Both are real. Both tell you something about the object, but they tell you different things. And if you confuse one for the other, you will end up with a mental model of a galaxy that is off by 100 trillion, which is what most people have, which is the lie we were born into, which is the correction that this walk is meant to undo. When you understand that the galaxy is bright because it has 100 billion bright stars, not because those stars are close together, the universe starts to make more sense. You stop being surprised that light takes a long time to travel from one star to another. You stop being surprised that interstellar travel is hard. You stop being surprised that the search for extraterrestrial civilizations has not yet produced results. The emptiness of the galaxy is the reason all of these things are true. The emptiness of the galaxy is the geometry of the situation. It is the actual shape of the place we live in. Part 9. What darkness means at cosmic scale. There is a word that astronomers use carefully, a word that does not quite mean what it means in ordinary English. The word is dark. When an astronomer says that a region of space is dark, they do not necessarily mean that no light is there. Light is almost always somewhere. What they mean is that the region contains no bright sources, no stars, no galaxies, no hot gas clouds, nothing that emits enough radiation to be detected by a given instrument. Darkness, in the astronomical sense, is a statement about the absence of sources, not about the absence of photons. The galaxy, by this definition, is mostly dark. Most of the volume of a spiral galaxy is not occupied by any bright source. The dark regions between the stars, the interstellar medium, is transparent and mostly empty. It is crossed by photons from the bright sources, photons that pass through it and continue on their way, but it does not itself produce light. It does not glow. It does not shine. It is dark in the astronomer's precise sense of the word, and the darkness, measured as a fraction of the galaxy's volume, is enormous. The fraction of a typical spiral galaxy that is occupied by actual stars, by the physical bodies of hot, glowing suns, is a number so small that it is easier to state as a ratio. The ratio of stellar volume to galactic volume for the Milky Way is about 1 part in 10 to the 20th, 1 part in 100 billion billion. That is the fraction of the galaxy that is stars. The other 99.99999999999% is empty. Let that land for a second. 99.9 followed by 10 more 9% of a galaxy, by volume, is empty space. If you want to find stars, you have to search. If you want to find empty space, you only have to point, anywhere, any direction. Most of the volume is empty. The stars are exceptions, bright points scattered across a vast darkness that constitutes the actual substance of the galaxy. Part 10. The Solar System as a Scale Model. Before we keep zooming out into the galaxy, let us zoom in one more time past the star into the solar system itself. Because the solar system contains, in miniature, the same lesson we have been walking through on the galactic scale. The solar system is mostly empty space. The objects in it, including the sun, including the planets, occupy such a tiny fraction of the total volume that the mental picture most people carry of the solar system is, again, wrong by orders of magnitude. The sun, at the centre, has a radius of about 700,000 kilometers. That is a large object. Not the largest object in the universe, not by a long stretch, but large by any planetary standard. The Sun's radius is about 109 times the radius of the Earth. If you scaled the Sun down to the size of a basketball, the Earth would be a pea about 26 meters away, and Neptune, the farthest planet, would be a marble almost 800 meters away. That is the scale of the planetary part of the solar system. At a basketball-size sun, 800 meters, a marble in a field, the furthest planet. Most of what is in between is empty. Between the Sun and Mercury, empty. Between Mercury and Venus, empty. Between Venus and Earth, empty. Between Earth and Mars, empty, except for the asteroid belt, which is itself so sparse that space probes can be flown through it without any special precautions because the odds of hitting anything are vanishingly small. Between Mars and Jupiter, vast emptiness. Between Jupiter and Saturn, emptiness. And on outward, through Uranus and Neptune, and out into the Kuiper belt, and out into the scattered disk, and out into the Oort cloud, all the way to the edge of the Sun's gravitational influence, which is somewhere around 2 light years from the Sun itself. 2 light years. That is the scale of the Sun's domain. From the centre of the Sun outward to the farthest icy bodies that still orbit it is about 2 light years of mostly empty space. And the outer part of that volume, the Oort cloud, is so sparsely populated that current estimates place the density at less than 1 cometary body per cubic kilometre in the densest regions, dropping to less than 1 per 1,000 cubic kilometres in the outer reaches. A person could stand on an Oort cloud comet and see, most of the time, nothing but the distant sun, a bright point no brighter than a typical planet viewed from Earth, and beyond it, the unchanging backdrop of the stars. This is what the solar system actually looks like. Not the textbook diagram where the orbits of the planets are drawn as concentric circles on a single page, creating the impression of a compact assembly. The textbook diagram is a schematic, not a map. The real solar system, laid out at true scale, stretches across a volume of space almost unimaginably larger than the sum of the sizes of the objects in it. Between each planet is an interval of emptiness so vast that spacecraft have to coast for years to cross it. Between the outer planets and the heliopause is an even larger interval. Between the heliopause and the next star is an interval larger still, and the emptiness of the solar system is not empty of things. It is just empty enough that, on human scales, the things are effectively undetectable. A few comets, here and there, a scattering of dust, a very thin solar wind, gradually losing pressure as distance from the sun increases. The occasional interstellar object that drifts through from outside, like Oumuamua in 2017 or 3I/Atlas more recently. These are the things that fill the emptiness. They are so rare relative to the volume that for most purposes the solar system is a vacuum, punctuated by a few rocky and gaseous exceptions. This solar system, with its long intervals between planets and its even longer reach out to the Oort cloud, is nested inside an interstellar neighbourhood of 4 to 5 light years of near-perfect emptiness to the nearest other star. And that neighbourhood is nested inside a spiral arm of the galaxy, which is itself nested inside the galaxy as a whole. At every scale, the pattern is the same. A few bright or solid objects surrounded by vast volumes of nothing much. The hierarchy of emptiness repeats at every level of the zoom. Part 11. What Milkomeda will actually look like. 4 billion years from now, give or take, the Milky Way and Andromeda are going to collide. This is one of the few predictions in astronomy that can be made with real confidence, because we can measure Andromeda's motion toward us directly through Doppler measurements of its approach velocity and proper motion measurements of its sideways drift. The two galaxies are moving toward each other at about 110 kilometers per second. They are about 2.5 million light-years apart. Do the arithmetic, and the collision becomes inevitable on a timescale of a few billion years. But what does a galactic collision actually look like? This is where the emptiness we have been walking through becomes beautifully relevant, because a galactic collision, contrary to what the word collision implies, is not a crash. It is not a smashing. It is not two solid objects hitting each other and breaking apart. A galactic collision is the passage of two enormous, mostly empty volumes of space through each other, with the occasional gravitational perturbation and almost no direct physical impact. When Andromeda and the Milky Way collide, the stars of each galaxy will pass through the stars of the other galaxy without any of them, statistically, touching. The probability of a direct stellar collision during a full galactic merger is so small that astronomers can calculate it exactly, and the answer is that you would expect, at most, a handful of stars out of the combined hundreds of billions to end up within grazing distance of each other. In most cases, even those near encounters would be passages at distances much larger than the sizes of the stars themselves. Two stars, Flying past each other at a distance of a few astronomical units is a near miss by astronomical standards, and a near infinite distance by any human standard. What will be disturbed is the gas. The diffuse interstellar medium of the two galaxies will collide and mix, and where clouds of gas are swept together at high relative velocities, shock waves will compress them and trigger new episodes of star formation. The collision will light up each galaxy with bright new clusters of young, hot stars. It will reshape the dust lanes. It will produce streamers and tidal tails of gas and stars pulled out of the two galactic disks by gravitational interaction. Viewed from outside, the two galaxies will look disrupted, dramatic, beautiful, reconfiguring themselves into strange new shapes over hundreds of millions of years. And viewed from inside, from a planet orbiting a sun-like star somewhere in the Orion Arm, the collision would be largely imperceptible on a human timescale. The sky would slowly change over millions of years as Andromeda's bright core grew visibly larger in the night sky, eventually overlapping with and then merging with our own galactic band. But no sudden events. No near misses, no explosions, just a slow, majestic rearrangement over spans of time that make human civilization look like a frozen moment. The final product of the merger, sometimes called Milkomeda, will be a single, large, elliptical galaxy, formed from the combined populations of both parent galaxies. The spiral structure will be gone, disrupted by the merger. The disk will have settled into a more spherical, more diffuse arrangement. The supermassive black holes at the center of each galaxy will eventually sink toward the center of the merged system, and, over another long interval, spiral together and merge into a single, larger black hole. The new galaxy will shine for tens of billions more years, slowly using up its gas, slowly fading as its young stars age. And throughout this entire transformation, the stars themselves will remain separated by the same kinds of distances we have been measuring: 4 light years, 7 light years, 10 light years. Whatever the exact spacing, the fundamental geometry will not change. Stars in Milkomeda will be as isolated from their neighbors as stars in the present-day Milky Way. The merger will not make the galaxy denser in a meaningful sense. It will make it larger. It will make it more structurally chaotic at first and then more settled. But it will not resolve the fundamental emptiness that defines every galaxy. The emptiness is not an accident of the Milky Way's current configuration. The emptiness is a feature of what galaxies, in general, are. If anyone is still on Earth in 4 billion years, and if they are still looking up at the sky on clear nights, the sky will be more spectacular than ours. Andromeda will be overhead, a vast glowing wash of light covering a quarter of the heavens. The two galaxies will be visibly interacting, their structures distorted by gravity into new shapes. New stars will be forming in bright clusters visible to the naked eye. The galactic merger, which is a catastrophe only on the largest cosmological scales, will be, from any inhabited planet, a slow light show that nobody will live long enough to see the whole of. Generations of observers will pass the knowledge of what is happening down to their descendants, who will watch the next incremental change, who will pass it on to theirs. The merger will unfold on timescales that dwarf any civilization, and inside all of this grandeur the same lesson will hold. The galaxies are mostly empty. The collision is mostly the interaction of gas and gravity, not the interaction of solid matter. The stars, even during the most violent phase of the merger, remain isolated. The emptiness preserves them. Part 12. Why we have not heard anyone else. The emptiness of the galaxy is, among many other things, a partial answer to a question that has puzzled scientists and philosophers for decades. Where is everybody? The galaxy is old. The galaxy is large. The galaxy contains, on current estimates, something like 10 to the 10th potentially habitable planets. Civilizations, if they arise with any regularity, should have had time to develop, to spread, to signal. And yet, across the decades that we have been listening for signals from other civilizations, we have heard nothing that we can confirm as artificial. No broadcasts, no structured signals, no unambiguous markers of technological activity. Silence. The emptiness we have walked through in this video does not answer the question by itself, but it provides a piece of the context that any answer has to fit into. Here is the piece. Even if there were a technological civilization transmitting at the power of our most powerful radar transmitters, operating on another planet orbiting another star in the Milky Way, the signal reaching Earth would be, by the time it arrived, extraordinarily faint. A civilization 1,000 light-years away, broadcasting at our current power levels, would produce a signal at Earth that is below the detection threshold of every radio telescope currently operating. A civilization 10,000 light-years away, operating at our power levels, would be completely undetectable with existing technology. The distances are the problem. The emptiness is the problem. The galaxy is large, and signals weaken as they spread out across that largeness, according to the inverse square law of radiation propagation. A signal strong enough to be heard across a galaxy's spanning distance would need to be intentionally, ferociously powerful, orders of magnitude more powerful than our own strongest transmitters, designed specifically to reach across the emptiness. And there is no reason to assume that every civilization out there has chosen to build such beacons, or has the energy budget to power them, or has survived long enough as a technological society to maintain them. The emptiness of the galaxy is not a proof that we are alone. It is a reason that, even if we are not alone, we might still not have heard anyone. The silence we experience when we listen to the sky is consistent with many different realities. A universe in which life is extraordinarily rare, a universe in which life is common, but intelligence is rare. A universe in which intelligent life is common, but technological civilization is rare. A universe in which technological civilization is common, but sustained broadcasting is rare. A universe in which broadcasting does occur but is drowned in the background noise of the galaxy, undetectable to our current instruments. Each of these possibilities is, in its way, a different face of the same geometric fact. The galaxy is large. The stars are far apart. Light and signals weaken as they travel. The emptiness of the medium is what shapes all of it. Before we can answer the question of whether anyone else is out there, we have to accept that the place we are searching in is so vast and so empty that finding a single whisper against the quiet is harder than most people have intuitively understood. The emptiness is not a verdict on cosmic loneliness. The emptiness is the background against which any search has to take place, and it is the reason that the search has been, so far, so unfruitful. Not because nothing is there necessarily, because nothing is close enough and loud enough and aimed in the right direction and arriving at the right moment to have reached our ears yet. This is the second-order meaning of the emptiness we have been walking through. The galaxy is mostly nothing, and the nothing has practical consequences for the kinds of questions we are able to ask and to answer. It shapes our isolation, It shapes our silence. It shapes the honest limits of what we can know about the rest of the universe, from the small position we occupy within it. Part 13. The photon's journey. Let us end the zoom the way we began it, but reversed. We started by imagining a photograph of a distant galaxy collapsed onto a pixel, and we unpacked what was actually inside that pixel. Now let us follow the reverse path. Imagine a photon emitted from the surface of a star somewhere in the disk of the Milky Way. That photon's journey, from the moment of emission to the moment of absorption or escape, is a journey through the emptiness we have been describing. Let us walk with it. The photon is born in the photosphere of a star. The photosphere is a thin layer, only a few hundred kilometers deep, where the star's interior plasma becomes transparent enough for light to escape. Inside that layer, a photon is produced by the relaxation of an electron from a higher energy level to a lower one, or by thermal emission from hot ionized gas, or by some other microscopic process. The photon leaves the photosphere moving at the speed of light, heading in a direction that is more or less random with respect to the star's surface, but becomes, from the star's perspective, a beam radiating outward into space. The photon passes through the star's chromosphere, a low-density layer above the photosphere, where the temperature rises mysteriously, and then through the corona, an even hotter and even less dense outer atmosphere where the solar wind is launched. Within a few stellar radii, the photon is in the solar wind, moving outward through a medium that, while very hot, is also very thin. The photon is moving fast enough that it has effectively left the star and is now in interstellar space, or very near it. For the next many years, depending on which direction the photon is heading, it will travel through the interstellar medium without encountering any substantial obstacle. If it is heading toward another star, it will eventually, in most cases, reach a zone near that star where the density begins to rise again, and it will either be absorbed by a particle or scattered. But for most photons emitted in most directions, the journey is much longer. The photon crosses light year after light year of almost perfect vacuum, passing through dust grains, passing through hydrogen atoms, passing through the tenuous mist of the interstellar medium without interaction. The photon keeps going. Eventually, the photon may reach the edge of the galaxy, leaving the disk, entering the galactic halo, an even lower density region occupied by old stars, globular clusters, and dark matter. The photon traverses the halo, again without substantial interaction, and then exits the galaxy entirely, entering intergalactic space. And intergalactic space is emptier still, orders of magnitude emptier than the most diffuse regions of the galactic disk. A place where the photon may travel for hundreds of millions of years without encountering anything meaningful. If the photon is heading in the right direction, it will eventually reach another galaxy. It will encounter that galaxy's outer halo, then its disk, then its interstellar medium. It will, again, in most cases, cross through without interaction and exit the other side. Or, more rarely, it will be absorbed by a star, or a planet, or a telescope. If the photon lands on a telescope, it gets counted. It becomes a data point. It arrives at the sensor and contributes a single unit of brightness to a single pixel of an astronomical image. That is the journey. From the photosphere of a star in one galaxy, across interstellar space, across intergalactic space, across perhaps another galaxy's disk, to the sensor of a telescope on a planet orbiting another star in another spiral arm of another galaxy. A journey of millions of light years, a journey of millions of years, And in all that time, in all that distance, the overwhelming fraction of the photon's path is through emptiness, vacuum, interstellar medium, intergalactic medium, almost nothing. The photon passes through almost nothing on its way to the sensor. And when we look at a deep field image, we are looking at the photons that made this kind of journey and happen to end up at our telescope. Each of those photons has a story. Each of them is a survivor. Each of them has traveled across volumes of emptiness that humans cannot directly grasp, carrying with it information about the star that emitted it, the galaxy that contained the star, the epoch of cosmic history during which the photon was born. And all of this information is available to us now, because the emptiness is transparent, because the galaxy is mostly nothing, because light can travel across galactic distances without being interrupted. The emptiness is not a deficiency. The emptiness is what makes astronomy possible. A denser galaxy would absorb its own light. A denser universe would be opaque. The visibility of the sky, the transparency that allows us to see galaxies billions of light years away, is a direct consequence of the fact that space, at every scale, is mostly empty. The same emptiness that isolates stars from each other and civilizations from each other is also the emptiness that allows light to reach us from the edge of the observable universe. We can see deep because the universe is thin. We are alone because the universe is thin. Both facts come from the same geometry. This is the balance we live inside. The galaxy is mostly nothing, and the nothing lets us see everything. The nothing lets photons travel for billions of years without being stopped. The nothing lets the sky on a dark night be filled with the light of stars whose emission events are millions or billions of years old. The nothing connects us across enormous distances to every luminous object in the cosmos. And the nothing also holds us apart from every other possibly inhabited world, making us isolated, making our search for company difficult, making the reality of cosmic loneliness, whatever its ultimate shape, a consequence of the same thin geometry that makes astronomy possible in the first place. Every time you look at a galaxy, remember this: the galaxy is mostly nothing. The nothing is what makes the galaxy visible. The nothing is what makes the journey of its photons possible. The nothing is the actual substance of the universe. The stars are the rare, beautiful exceptions to the larger rule of quiet and distance. And we, here, on Earth, under our thin blue sky, are one of those rare exceptions looking up at all the others, across the vast, transparent emptiness that separates us and connects us at the same time. Part 14. The dark halo you cannot see. There is a piece of the galaxy we have not yet talked about, and it is, in terms of mass, the largest piece of all. Everything we have been zooming into so far, the stars, the interstellar medium, the spiral arms, the disk, the central bulge, all of that together accounts for roughly 15% of the total mass of the Milky Way. The other 85% is something else, something that does not emit light, something that does not interact with electromagnetic radiation of any kind that we have been able to detect, something that, in terms of the emptiness we have been measuring, adds a new layer to the question of what the galaxy actually is. It is called the dark matter halo, and it surrounds the visible galaxy in a roughly spherical cloud that extends far beyond the disk, far beyond the visible halo of globular clusters and old stars, far beyond any point you would mark on a photograph as the edge of the galaxy. The dark matter halo of the Milky Way, based on the kinematics of satellite galaxies and the rotation of the outer gas disk, extends out to roughly 300,000 light-years from the galactic center. That is 3 times the diameter of the visible galaxy. A sphere of invisible gravitating material, holding the whole visible structure inside it like a walnut inside a large piece of fruit. What is dark matter made of? We do not know. We have been searching for decades. We have built detectors deep underground to look for the rare interactions of dark matter particles with ordinary atoms. We have built particle accelerators to try to produce dark matter candidates in controlled collisions. We have stared at the cosmic microwave background and at the rotation curves of galaxies, and at the structure of galaxy clusters, all looking for signatures of what the dark matter is. And after 40 years of this work, we know what dark matter is not more than we know what it is. It is not ordinary matter. It is not any of the 3 known neutrino flavors. It is not dead stars or faint red dwarfs or rogue planets. It is some new form of matter that the standard model of particle physics does not contain. Whatever it is there. Its gravitational effects on the visible galaxy are the most robustly documented observations in modern cosmology. The outer parts of spiral galaxies rotate faster than they should if only the visible matter existed. The velocity dispersion of galaxies inside clusters is higher than it should be based on the visible mass alone. The gravitational lensing produced by clusters bends light more than the visible mass can account for. Every independent line of evidence points at the same conclusion. There is more there than meets the eye, and the more than meets the eye is the dominant component of the galaxy's mass. Now consider the implications for the emptiness we have been walking through. We said earlier in this video that about 99.9 followed by 10 9% of the galaxy, by volume, is empty. That calculation considered only the visible matter, the stars and the gas and the dust. It did not consider the dark matter halo. The dark matter halo is even more diffuse than the visible matter. It does not clump into stars. It does not concentrate into dense clouds. It spreads itself across the entire halo volume, thinly, smoothly, a roughly uniform distribution that extends hundreds of thousands of light-years in every direction. The density of dark matter in the solar neighborhood is about 0.4 gigaelectronvolts per cubic centimeter. In more everyday units, that works out to roughly 1 dark matter particle of the kind most theories predict, every few cubic centimeters. A handful of particles per liter of space, thinner than the air we breathe by a factor almost too large to state cleanly. And this density is the highest you find anywhere near the Sun. Further out in the halo, the density drops further still to values that approach 0 at the outer edge. The dark matter, in other words, makes the galaxy larger than we see and fills that larger volume with an extra form of emptiness. A different kind of emptiness, an emptiness filled with something, yes, but something whose somethingness is so faint and so diffuse that it cannot be seen, cannot be touched, cannot be interacted with by any of the chemistry of life. The dark matter halo is there. We know it is there. We cannot see it. We cannot feel it. And the galaxy, properly understood, is not a structure that ends at the outer edge of the visible disk. The galaxy is the whole halo, extending 3 times further than the visible part, filled with a ghostly presence that we infer but cannot directly observe. This is another layer of what the galaxy looks like when you zoom in. Not just mostly empty in the sense of having vast gaps between stars, also extending into an even larger volume where the dark matter lives, which is itself almost perfectly empty, which contains the bulk of the galaxy's mass but produces none of its light. The galaxy is a bright, small visible part embedded inside a vast invisible part, and the invisible part is, by mass, by volume, by any reasonable accounting, the actual galaxy. The visible part is the tip of the iceberg, the glow that emerges from the bulk. Every time you look at a galaxy photograph, remember that you are seeing only the luminous fraction of a much larger structure. The structure you see is embedded inside a dark halo that extends 3 times further than the picture shows. The picture captures the bright part. The actual galaxy includes the part that does not photograph. Part 15. The scale of the whole zoom. Let us take one last walk. Start with a photograph of Andromeda hanging on a wall. In the photograph, the galaxy is a bright pinwheel, about the size of a dinner plate. It is dense, it is packed, it is beautiful, and it is deeply wrong about its own geometry. Let us imagine now that we could walk into that photograph, that we could step through the print and onto the surface of the image at the edge of the visible disk and begin to explore. At first, nothing seems strange. The photograph at the scale of the entire galaxy is a reasonable summary. As we begin to move toward the center, we see spiral arms resolving out of the general glow. We see bright clusters emerging from what had looked like smooth gradients. We see dark lanes of dust threading through the brightness, unmistakably showing the texture of the disk. The galaxy is starting to look real, but then we zoom in further. We pick a spiral arm and we zoom past the clusters, past the bright pockets of star formation, into the space between the clusters. And what was brightness at the broad scale becomes, at this scale, darkness threaded with distant points of light. The arm itself, which at zoomed-out scale looked like a continuous glowing river, resolves into mostly space, sprinkled with stars that are, at the resolution we have reached, separated from each other by distances that feel impossibly large. We keep zooming. We pick one of the distant points. We move toward it. The point resolves into a star, and the star turns out to have a solar system of its own, with planets and moons and asteroid belts and comet clouds. And we zoom further. We pick a planet, we move toward it. The planet resolves into a world with continents and oceans and clouds and weather. And we zoom further, and we land on the surface. And we find, if the planet is the right kind, grass and trees and animals and perhaps even people, and if one of those people is looking up at the sky, we realize that we have closed the loop. The sky they are looking at is the same sky we are looking at, the same galaxy, the same vast empty structure. The whole zoom is possible because of the emptiness. Every step we took, we were moving through mostly empty space. Between galaxies, empty. Between stars in the galaxy, empty. Between planets in the solar system, empty. Between moons and asteroids, empty. The zooming through is possible because the structure is, at every scale, dominated by vacuum. The objects are exceptions, small, dense things embedded in much larger volumes of nothing. The emptiness is the medium through which everything moves. And now, here is the final question. If we started on the surface of a planet, zoomed out through the solar system, through the galaxy, through the universe, all the way back to the photograph hanging on a wall, what have we learned about the photograph? We have learned that the photograph is a projection, a compression, a summary of a vastly more complicated three-dimensional reality. The photograph is not wrong in the sense of being fabricated. It is accurate about the total brightness of the galaxy, integrated over the frame. But it is misleading about the density of the galaxy, about the spacing of the stars, about the sheer emptiness of the medium those stars are embedded in. The photograph tells you something true and, at the same time, hides everything else. This is the paradox of astronomical imaging. The photographs are honest, and the photographs are misleading. Both are true. The photographs record the light, and the photographs cannot record the space. The photographs are the only representation of distant galaxies we will ever have, and they leave out the thing that defines those galaxies more than anything else: the emptiness. If we want to know what a galaxy really is, we have to supplement the photograph with the walkthrough. We have to do what we have just spent an hour and 45 minutes doing. We have to zoom, we have to measure, we have to count the stars and calculate the distances and translate the numbers into metaphors we can feel. We have to build inside our own minds a model of the galaxy that is not constrained by what a camera can capture. This is not easy work. The mental model requires effort. It requires holding in the imagination volumes and distances that our ancestors had no occasion to develop intuitions for. But the work is worth doing. Because the real galaxy, the one with all the emptiness restored to it, is a more honest object than the galaxy of the posters. The real galaxy tells us something accurate about where we live. The poster galaxy, however beautiful, tells us something that is not quite true. And you are allowed to carry both in your head. You can love the photographs, you can enjoy the spiral arms of Andromeda, or the whirlpool, or the sombrero, rendered in all their compressed glory on the pages of books and the screens of computers. You can have those images, and you can still also have the knowledge that behind each image is a reality far stranger, far lonelier, far emptier than the image itself can show. Part 16. The exceptions to the emptiness. Everything we have walked through so far has been about how empty a galaxy is. The vast gaps between stars, the sparse interstellar medium, the dark halo that extends invisibly outward, the almost perfect vacuum through which light travels for millions of years without interruption. That has been the thesis. That has been the correction to the poster picture. But there are exceptions. There are places inside a galaxy where matter does concentrate, where objects do sit close together, where the emptiness gives way to something denser. Those exceptions are worth walking through because they help define the rule. They show you what a galaxy looks like when, for once, it is locally crowded. And they help you understand why the rest of the galaxy, by contrast, is as empty as it is. The most important exceptions are called globular clusters. A globular cluster is a tightly bound, spherical collection of stars, typically containing anywhere from 100,000 to 1,000,000 members, all gravitationally bound into a compact ball, roughly 100 light-years across. Globular clusters are found mostly in the halo of a galaxy, orbiting the galactic center on long, slow, eccentric paths. The Milky Way has about 150 known globular clusters. Other large galaxies have more. What makes a globular cluster dense? The answer is that a lot of stars are packed into a small volume. A typical globular cluster has, in its core, a stellar density hundreds to thousands of times higher than the density of stars in the Sun's neighborhood. In some extreme cases, the core density can exceed 1,000 stars per cubic light-year, compared to roughly 1 star per 250 cubic light-years in the Sun's neighborhood. If you lived on a planet orbiting a star in the dense core of a globular cluster, your night sky would be different from ours in ways that are hard to imagine. Instead of a handful of visible stars at naked eye brightness, you would see thousands of bright stars distributed across the sky, many of them so close that they would appear to your eye as nearly disks rather than points. The night would not really be dark. The combined starlight would illuminate the ground faintly, casting soft, multi-directional shadows. Astronomy, as a science, might never have developed on such a world. The sky is too bright to see beyond it. But even here, even inside the densest concentrations of stellar matter that galaxies produce, the emptiness has not gone away. It has only been compressed. 1,000 stars per cubic light year means that the typical distance between stars in such a cluster is about 1/10 of a light year, or roughly 1,000 times the Earth-Sun distance. That is still, by any Earth standard, an enormous distance. 1/10 of a light year is roughly 6,000 astronomical units. It is further than the outer edge of the Oort cloud. A star and its nearest neighbour in a dense globular cluster core are still separated by a gulf that exceeds the entire range of our solar system, many times over. Globular clusters are the denser exception, and even the dense exception is mostly empty. The ratio of stellar volume to cluster volume, even inside the densest cores, is still effectively zero by any human intuition. The stars are closer than they are in the Sun's neighbourhood, but closer in this context still means thousands of times further apart than any terrestrial scale. The galaxy, in other words, cannot escape its own geometry. Even in its most concentrated regions, the gaps between things are still enormous. The emptiness is not a feature of a particular location. The emptiness is a feature of galactic structure everywhere. Outside the globular clusters in the much larger volumes of the galactic disk and halo, the density falls back down to the numbers we have been using throughout this video. 1 star per few hundred cubic light years, 1 atom per cubic centimetre of interstellar gas. 99.9 followed by a long string of nines, % of the volume empty by any reasonable measure. The globular cluster is the exception that proves the rule. Even the denser places in the galaxy are not dense, they are only relatively dense, and the relative density is still, by any honest measurement, almost indistinguishable from vacuum. Part 17. The galactic centre up close. There is one place in the galaxy where the density does become genuinely dramatic. It is the central few light years around the supermassive black hole at the heart of the Milky Way, a region that contains the object officially designated Sagittarius A star. This is the densest stellar environment in our galaxy, and it is in some ways the most extreme environment any known astrophysical structure produces short of the interiors of stars themselves. Sagittarius A star is a black hole of about 4 million solar masses. It sits, as far as we can tell, almost perfectly still at the gravitational centre of the Milky Way. Around it in orbit is a dense population of stars called the S-cluster, which contains perhaps a few dozen massive young stars and an unknown but probably much larger number of fainter, older ones. These stars orbit Sagittarius A star on highly elliptical paths, some of them swooping in to within a few times the Earth-Sun distance of the black hole at closest approach, then racing back out to distances of thousands of astronomical units before swinging in again. Their orbital periods range from a few years to a few decades. If you could visit the centre of the galaxy, standing on a hypothetical platform in stable orbit around Sagittarius A star, the view would be unlike anything you have ever seen. The sky would be filled with stars, not a few thousand as on a dark Earth night, but tens of thousands, packed together so densely that entire regions of the heavens would appear as continuous sheets of starlight. Through this blaze of stellar activity, the black hole itself would be invisible to the naked eye, marked only by the peculiar way the stars moved around an apparently empty region of space, their orbits betraying the presence of something enormous and dark at their center. This is, among all the regions of the galaxy we could visit, the one that most resembles the popular mental picture of what a galaxy looks like. A dense sky, a crowded environment, a place where the stars are, in some sense, actually close together. And yet, even here, the emptiness persists. The density of stars in the central parsec around Sagittarius A star is roughly 100 million times the local stellar density in the Sun's neighborhood. 100 million times denser. That sounds impressive, but it still works out, by simple arithmetic, to an average distance between stars of about 1,000 astronomical units, or roughly 1/100th of a light year. Not much by galactic standards, still enormous by any Earth standard. Even in the densest stellar environment in the galaxy, stars are still separated by more than the full diameter of our own solar system. The central parsec is the exception to every other exception. It is the densest place in the galaxy, and it is still, at the honest measurement, empty space with scattered stars embedded in it. The fabric of the galaxy, even at the heart of its gravitational singularity, does not close ranks. The stars remain separated. The emptiness continues in attenuated form, all the way down to the event horizon of the black hole itself. Beyond that event horizon, the geometry of space changes. The emptiness question no longer applies in any ordinary sense. What sits inside the event horizon is, by definition, outside anything our current physics can describe. But even approaching that boundary from outside, the galaxy we see is recognizable. A scatter of stars in a mostly empty volume, brighter and denser here than anywhere else. Still, fundamentally, the same kind of structure. Part 18. Rogue planets and the invisible population. We have been talking about stars as if stars were the only kind of object that fills a galaxy. They are not. Galaxies contain, by estimates that have been growing steadily over the last decade, at least as many rogue planets as they contain stars. Rogue planets are gas giants, rocky worlds, or intermediate-sized bodies that are not orbiting any star. They drift through interstellar space on their own, unanchored, cold. Dark, mostly invisible to any current instrument short of a gravitational micro-lensing event. How do rogue planets form? Two main ways. The first is that they form the way any planet does orbiting a young star, but are then gravitationally ejected from their planetary system by interactions with other planets or with passing stars. The second is that they form on their own, by direct gravitational collapse from dense fragments of interstellar clouds, without ever having a host star at all. Both processes happen, both contribute, and the combined population of rogue planets in the Milky Way, based on micro-lensing surveys and theoretical modelling, is estimated at somewhere between 100 billion and 1 trillion objects, comparable to the total number of stars, possibly larger. What does this mean for the emptiness picture we have been building? It means that when we say the galaxy is mostly empty, we were being slightly generous about how crowded it is. In addition to the 100 billion stars and their handful of still-bound planets, there is an equal or larger population of free-floating dark worlds, some of which are Earth-sized, some of which are Jupiter-sized, all of which are effectively invisible, Every point in the galaxy, including the regions we think of as interstellar space, may contain at any moment a nearby rogue planet that we do not know is there. But even with this correction, even adding 1 trillion more bodies to the galactic inventory, the emptiness does not meaningfully shrink. The reason is simple. 1 trillion rogue planets sounds like a lot, and it is. But distributed across the volume of the galaxy, 1 trillion objects in 7 million cubic kiloparsecs of space works out to a density so low that the average distance between a rogue planet and its nearest neighbour is still several light years. A rogue planet is not typically close to any star. A rogue planet is not typically close to any other rogue planet either. The rogue planet population is, like the stellar population, a sparse scattering embedded in a vast emptiness. Adding them to the galaxy does not make the galaxy crowded. It just adds another layer to the same sparse arrangement. And this matters because it tells us something about what the honest inventory of the galaxy looks like. The galaxy is not just stars. The galaxy is stars, and brown dwarfs, and rogue planets, and ejected asteroids, and dust grains, and diffuse gas, and dark matter, all distributed at various concentrations across an enormous volume. Most of that volume is still empty. Most of the dark objects are still far from each other. The galaxy remains, at honest measurement, mostly nothing. But the mostly nothing is, if we are being thorough, slightly more populated than the star-only count suggests. There are dark, cold, lonely worlds drifting between the stars, moving through the emptiness on trajectories that may never bring them into close contact with any other significant object. They, too, are part of the inventory of what a galaxy is, part 19. The view from a ship that could travel between stars. Imagine as a thought experiment that we had built a spacecraft capable of traveling at 1/10 the speed of light. That speed is beyond our current technology by orders of magnitude. No propulsion system we have yet built or yet credibly designed could accelerate a macroscopic payload to that velocity. But suppose, for the sake of argument, that we had one. What would a journey between stars look like from the cabin of such a ship? The journey to Proxima Centauri, our nearest neighbour, would take about 42 years at 1/10 of the speed of light. 42 years of continuous flight. You would leave Earth. You would spend roughly a year accelerating. Then you would coast for 40 years through the mostly empty interstellar medium. Then you would decelerate, spending another year slowing down. And then, 42 years after departure, you would arrive in the Proxima Centauri system, ready to explore. What would you see during those 40 years of coasting? Almost nothing. The stars ahead of you and behind you would be slightly shifted in wavelength by the Doppler effect, blue shifted ahead and red shifted behind, but only slightly. At 1/10 the speed of light, the shift is modest. The stars would look basically like they look from Earth. The sun would appear as a bright yellow point, fading to a dimmer point, fading to a point you could barely distinguish from the other stars in the background. Proxima Centauri would appear as a dim red point, slowly brightening over the decades as you approached. Between these two endpoints, the view would be dominated by the interstellar medium, which is to say, by almost nothing. You might occasionally pass close enough to a dust grain to register its presence on sensitive instruments. You might cross regions of slightly elevated density, thin clouds of hydrogen gas that the ship's shielding would easily deflect. You would not see stars closer than the endpoints because there are no stars in between. The gap Between the Sun and Proxima Centauri, once you are inside it, is simply empty space stretching in every direction, with the two endpoint stars visible as distant points, and nothing else of significance to punctuate the view. 40 years of this. 40 years of almost identical view out every window of the ship. The stars drifting slowly across the sky as the ship's orientation and velocity gradually change. The Sun and Proxima Centauri, the two most important objects in the whole journey, both so distant for most of the trip that they are just points among points, and between them the emptiness, the void, the long patient crossing of a gap that, even at 1/10 the speed of light, takes decades of human time. This is what interstellar travel would actually feel like if we ever achieved the propulsion to attempt it. It would feel like emptiness. It would feel like a long, slow coast through almost nothing, with the occasional faint nebula or distant globular cluster visible as a small bright region in the distance, but nothing nearby, nothing touchable, nothing that would come close enough to be examined during the journey. The galaxy, at honest scale, is a place that punishes travellers with emptiness. Every trip is mostly coast. Every coast is mostly uneventful. Every destination is reached only after durations that strain biological timescales. We, as a species, have never taken a trip like this. Our longest human-scale journeys, the Apollo missions to the Moon, lasted about a week. The longest robotic missions, like Voyager and the Mars rovers, span decades but do not carry human crews. No human being has ever travelled for decades through mostly empty space toward a destination too distant to see clearly. And if we ever do, we will be doing it at the mercy of the galaxy's geometry. A geometry of vast distances, negligible densities, and long, slow crossings. A geometry that, whatever propulsion we invent, will always require time, will always require patience, will always remind us, through its unblinking emptiness, that the scale of what we are crossing is not a human scale. Part 20. The final measure. Let us try to say, in the simplest possible way, what a galaxy is when you zoom in all the way. A galaxy is a volume of space, roughly disc-shaped, roughly 100,000 light-years across, containing roughly 100 billion stars. Each star is, on average, about 5 light-years from its nearest neighbour. Each 5 light-year gap contains, for the most part, nothing. A thin mist of hydrogen and dust, yes. Occasional rogue planets, yes. A diffuse flux of cosmic rays and neutrinos and photons from all directions, yes. But no substantial mass. No solid objects. No places where a spacecraft could land. No structures that could be approached and examined. No matter that would resist the passage of an incoming beam of light. The galaxy, in this honest description, is not crowded. The galaxy is not packed. The galaxy is not a bright carpet. The galaxy is a sparse population of stars, each one brilliantly bright in its own right, but separated from its neighbours by gulfs of emptiness that no intuition native to Earth can fully hold. And the gulfs are transparent. The gulfs are thin. The gulfs are the medium through which all the light we see when we look up at the night sky travels, mostly unimpeded, from the stars that emitted it to the eyes or instruments that detect it. And inside this sparse arrangement we sit, on a small planet, around a small star, in a relatively quiet region of one spiral arm, looking out at the rest of the structure across the same emptiness that defines the structure, seeing only what is bright, because that is what our instruments can detect, missing most of what is there, because most of what is there is dark. The galaxy is mostly nothing. That is the summary, 5 words. Everything else we have said in this video is elaboration and evidence and context for those 5 words. A galaxy is mostly nothing, and the nothing is the substance. When you look up at the sky tonight on a clear night far from city lights, and you see the band of the Milky Way stretching from horizon to horizon, remember this: you are looking at a 2-dimensional projection of a 3-dimensional emptiness scattered with bright points. The bright points are the stars. The emptiness is the overwhelming majority of what is there. Your eye, in the act of seeing, is collecting the photons from the bright points and rendering them as a band of light. Your eye cannot render the emptiness. The emptiness is the part that your brain, looking at the photograph your eye has produced, has to imagine. Imagine it. Take a long breath and imagine the gulfs. Imagine how far one star is from the next. Imagine the transparent rivers of space through which the light is traveling toward you right now, having been in flight for hundreds or thousands or tens of thousands of years. Imagine the slow, patient, geometric structure of a galaxy at rest, rotating majestically around its center, hundreds of billions of tiny bright points held in place by gravity, separated by vast, silent volumes of almost perfect nothing. That is your galaxy. That is the thing you live inside. That is the structure whose outer rim is not the edge of anything, but the beginning of a larger emptiness stretching out to the next galaxy, and the next, and the next. That is the shape of the place you exist in, and you looking up at it are one of the rare points inside it where the matter has organized itself into something capable of looking up, of wondering, of measuring, of understanding what it is looking at. The galaxy is mostly nothing, and you are one of the small somethings embedded in it. That ratio, the ratio of the nothing to the something, is the shape of your situation. And understanding the shape, even incompletely, even for a few moments at a time, is what it means to take the sky seriously, to let the emptiness become as real as the brightness, to let the galaxy show itself honestly, instead of compressed into the dishonest summary of a photograph. Part 21. Beyond the galactic edge. We have spent this entire video inside a single galaxy, the Milky Way, our home. But there is one more piece of the emptiness picture worth saying out loud before we close, which is what happens when you leave the galaxy entirely. When you cross the outer rim of the visible disk and keep going outward into intergalactic space, what do you find? What you find, first, is the diffuse outer halo, old stars and globular clusters orbiting at great distances from the main disk, some of them 200,000 or 300,000 light-years out. These are the last stragglers, the final outer signs that you are still gravitationally tied to the Milky Way. The density of stars in this region is much lower than in the disk. Even by galactic standards, the outer halo is empty. You could travel for thousands of light-years in the outer halo without encountering any significant object. Keep going. Cross through the outer halo, cross through the edge of the dark matter halo, which stretches further still, and eventually you enter the truly intergalactic medium. And the intergalactic medium is emptier than anything we have described so far. The intergalactic medium has an average density of about 1 atom per cubic meter. 1 atom per cubic meter. That is thinner than the interstellar medium of the galactic disk by a factor of about 1,000. That is thinner than any laboratory vacuum we can produce with existing technology. That is closer to perfect vacuum than anything that exists anywhere on Earth. And this is what you have to cross to reach the next galaxy. 2.5 million light-years of it to get to Andromeda. More for any other large galaxy, The nearest galaxy cluster beyond our local group is the Virgo cluster, about 54 million light-years away. The distance from the Milky Way to Virgo is 54 million light-years of near-perfect intergalactic vacuum. If you think the galactic disk is empty, the intergalactic medium is emptier still, and if the intergalactic medium is empty, the cosmic voids, the enormous dark regions of space between superclusters of galaxies, are emptier again. The universe at the largest scales is not a continuous fabric, it is a web. Filaments of galaxies strung across voids of almost perfect nothingness, voids tens or hundreds of millions of light-years across, through which you could travel in any direction and encounter nothing. No galaxy, no cluster, no structure of any kind. The emptiness we have been walking through, the 99.9 followed by 10 nines% of the galaxy that is empty, is just a local sample of a pattern that extends all the way up to the largest scales of the universe. The universe, from the distance between stars all the way up to the distance between superclusters, is mostly nothing. At every scale we can measure, the density of luminous matter is vanishingly small compared to the total volume. At every scale, the rule holds. Emptiness is the medium. Brightness is the exception. This is the largest scale lesson the zoom can teach. When you zoom into the smallest scales, you find empty cubic parsecs with a single star embedded in each one. When you zoom out to the largest scales, you find empty voids with a single filament of galaxies embedded in each one. The structure is self-similar in its emptiness. At every scale of the universe, most of the volume is empty. The bright things are scattered sparsely across that emptiness. The ratios differ depending on the scale, but the qualitative picture does not change. The universe is mostly dark. The universe is mostly quiet. The universe is mostly space, with occasional luminous exceptions. And we, on our small planet around our small star in our relatively quiet arm of our relatively quiet galaxy, are one of those exceptions. We are a small bright something in a much larger, mostly empty field. We are, in cosmic terms, an outlier. A rare event, a corner of the universe where matter has clumped together densely enough and stably enough to support the kind of chemistry that eventually produces the kind of organism capable of looking up and noticing the emptiness. This is not a discouraging fact. It is a clarifying one. Understanding the emptiness at every scale does not make us smaller. It just clarifies where we are. We are where the matter is. The rest of the universe, which is to say most of it, is where the matter is not. And the contrast between where we are and where we are not is what gives our existence its particular shape. We are, all of us, inhabitants of the dense exceptions to the cosmic rule of emptiness. And from inside those dense exceptions, we look out at the rule itself. And we try, using instruments and imagination and patience, to understand what we are seeing. What we are seeing, if we let the zoom play out all the way, is a universe whose dominant feature is emptiness, whose most common substance is nothing, whose largest structures are voids, not filaments, and whose bright parts, the galaxies, the clusters, the stars, the planets, the organisms, are the minority condition. We are the rare case. And the rare case is where we live. The sky has a great deal to say right now, and it is saying most of it in silence. The silence is not the failure. The silence is the structure. It is the shape of what a galaxy is when you look at it honestly, at the resolution where individual stars can be separated, where the distances between them can be measured, where the emptiness between them can be counted. A galaxy is mostly nothing, and the nothing is the most important part of the answer. Not because the nothing is where the interesting things are, because the nothing is what makes the interesting things possible in the first place. Listen to the silence. Let the dark parts of the galaxy speak. Let the emptiness become as real in your mind as the bright points have always been. And then you will know what a galaxy actually looks like when you zoom in all the way. It looks like mostly nothing. It looks like light, scattered almost beyond the scope of any honest metaphor. It looks like the universe, which is the place, whether we remember it or not, that we have always lived,